In this video we keep working with this concepts of automorphisms and inner automorphisms. So I'm going to denote automorphisms this way now. So it will be automorphism of G and inner automorphisms. I'm going to write it this way. Okay, theorem. The automorphisms of G and the inner automorphisms of G are groups. The set of automorphisms of a group and the set of inner automorphisms of a group are both groups. Well, if you need for instance, well, not for instance, the automorphisms might be a complicated thing. The inner automorphisms of G is really easy. So let me just remind you that the inner automorphism of G is phi A of x, where A inverse times x times A. Okay, of course, for all x in G, and G is a group. Okay, so let G be a group and A be in G. A is also in G. The function phi of A, defined this way, phi A of x equals A inverse times x times A for all x in G, is called an inner automorphism of G. We say induced by A. So if you have a certain set G with elements like identity A, B, C, etc., and you want to find the inner automorphism of G, that's really easy, right? You just pick phi and you do phi of the identity, phi of A, phi of B, etc. It's really easy. Okay. Of course, this list might have some duplications. Okay, because phi of A might be equal to phi of B. Okay, even if A is different from B. Even if A is different from B, the phi of A might be equal to phi of B. There are plenty of examples of this. Okay, and this is an excellent exercise. You can find a group G where A is different from B, but the automorphism, the phi of A and phi of B are the same. Okay. So the only thing you have to do in order to find the inner automorphism of G is to, well, this is brute force, right? First you get all phis, and when you get all phis, then you check which ones are equal, and then you take, for instance, you take this one, you take the ones that are equal, and you just found the inner automorphism of G. Really easy. If you want to determine the automorphisms of G, this might be a bit more difficult. In the previous example, I worked on the inner automorphisms of D4, but in my previous example, this automorphism was induced by the rotation of 90 degrees. If you want the inner automorphism of D4, and we can consider this an example, an inner automorphism of D4, but induced by the rotation of 180 degrees, everything is going to change. Because now you have phi of x of rotation 180 degrees, right? So you will have the rotation of 180 degrees in the inverse sense, then x, and then rotation of 180 degrees. Okay, so V4 was, and it is the set with rotation 0, rotation 90 degrees, rotation 180, rotation 270, if I remember well, horizontal rotation through horizontal line, vertical line, first diagonal, second principal diagonal, second diagonal. Okay. Of course, we will have inner automorphisms. With any of these, it can be phi of the identity, phi of rotation of 90 degrees. We did that in the previous video. Rotation of 180 degrees. Phi of this rotation, phi of rotation of 270 degrees. Phi of rotation through the horizontal line, etc. Now let us take an inner automorphism. We did that with rotation of 90 degrees in the previous video. Now let us think of the phi of rotation, the inner automorphism induced by the rotation of 180 degrees. This one here. So that will be phi rotation of 180 degrees, element x is going to be rotation in the inverse sense, x, and rotation 180 degrees. Okay. Let us pick any element, for instance, x, this one, x. So if we pick this one, okay, phi rotation of 180 degrees through element x, any element. So we rotate to the left, times x, times rotation to the right. So this will be x, right? Okay. Now, let us do this one too. Phi of rotation of the identity rotation, 0 degrees rotation. That will be 0 degrees rotation to the left, x, 0 degrees rotation to the right. Oh, but that's x too. So you see, these two, they are equal. So this means that the rotation of 100, phi, the automorphism induced by the rotation of 180 degrees is equal to the phi induced by the rotation of 0 degrees. Okay? And now it's a real simple exercise to check the rotation of 270 degrees, this automorphism. It will be the same as phi of rotation of 90 degrees. Okay? This is easy to check. Okay? So, and you will have some others like the phi induced by the rotation through the horizontal line will be equal to phi induced by the rotation through the vertical line. Okay, and phi induced by the main diagonal, it will be equal to phi induced by the second diagonal. Okay, so if we want all the automorphisms, taking these elements that repeat, we have phi of zero rotation, phi of rotation of 90 degrees, phi of the main diagonal, and etc. Okay, and you check which one repeats and which one doesn't. Okay, and you'll get all the list of the inner automorphisms. There's the list of all the inner automorphisms of D. Phi, I have a mistake here. Okay, I'll correct that mistake. I'll finish this first. So the list of all the automorphisms, it will be phi of rotation of 0, phi of rotation 90 degrees, phi of rotation through the main diagonal, and phi of rotation through the second diagonal. There's something wrong here. Phi of these two are not equal, because no, these two are not equal. I'm sorry, I'm going to write the correct thing. The second diagonal equals the main diagonal through rotation of 180 degrees. I don't know what I said here, but there was something wrong here. Okay, there was something wrong here, because these are the real list of the so you can pare down the list to these automorphisms, these four automorphisms. You can check that these four are distinct and all the others equal one of these. Okay, so let us take another example. I'm going to call it example 2. Maybe we could take this time the automorphism around one of the z's, let us say z10. Okay, so we are going to compute the automorphism of z10. Z10, I choose Z10 because it's really a very simple group under addition module 10, right? So we have 0, 1, 2, 3, etc. till 9, right? Okay, do not forget that this is Z10 under addition module 10. Okay, so if you want to find the automorphisms of Z10, I like to think this way. Imagine you have 0, 1, 2, 3, 4. So if you if every the order of Z10 will be 10, right? Okay. Now, if you multiply every single element by 1, you'll get 0, 1, 2, 3, 4. So this is clearly you're getting the identity here. So if we call alpha a candidate to, we have to discover enough information about alpha to determine how alpha must be defined. Okay, so in Z10 is really simple. So for instance, if you have k of alpha, you have 1 plus 1 plus 1 alpha, and this will have k terms. Okay, that means 1 alpha plus 1 alpha plus 1 alpha, that is k 1 alpha. Okay, so we need only to determine the choices for 1 alpha to make alpha an automorphism of Z10. I don't know if I'm being very clear here, but here I have a problem. Do not forget this, one of the properties of the isomorphisms was that the order of alpha has to be equal to phi of alpha. Okay? And that's why I like to see it this way, because if I multiply all the Z10s by 1, I get 1 times 0, I get 0. 1 times 1, I get 1. 1 times 2, I get 2. So if my alpha is 1, okay, if I have 1 alpha equals 1, the order here is going to be 10, because I'm going to get 10 elements here. But imagine you do 2 alpha. What about 2 alpha? If you multiply 2 times 0, you get 0. 2 times 1, you get 2. 2 times 2, you get 4. 3. 2 times 4, 8. 2 times 5, you get 0. Right? This is module 10. 2 times 6 is 12. 9, 10, 11, 12. You get 4. Okay. 2 times 7, you get 14. So 9, 10, 11, 12, 13, 14. You get 8. 16. So you get 4. No, wait a sec. I'm doing something wrong here. So 2 times 5, you get 10. 9, 10, that's 0, right. 2 times 6, you get 12. So 9, 10, 11, 12. You get 2. This one is 2, right? Yes, I'm going to erase this. I was doing stupid things here. So this is 2. 2 times 7, you get 14. 9, 10, 11, 12, 13, 14. Okay, you're getting 4. And here you get 6, and here you get 8. Okay, so check the order. 1, 2, 3, 4, 5. The order here is 5. The order of 2 alpha is 5, so it's not 10. Okay, so 2 cannot be an automorphism. Okay, but 1 can. Okay, so it's easy to check that your candidates to automorphisms is 1, 3, 7, and 9. You can check this. Okay, so I'm going to call this alpha 1, alpha 3, alpha 7, and alpha 9. Okay, and here we have all the automorphisms of Z10. So in previous videos we saw that the table for U10, the group of units module 10, the set of integers less than 10 and relatively prime to 10 under multiplication module 10. Okay, so we saw this, right? And now we just saw the automorphisms of Z10, and we saw that that was alpha 1, alpha 3, alpha 7 and alpha 9. Okay, so this is the automorphisms of Z. So the automorphisms of Z10, alpha 1, alpha 3, alpha 7, alpha 9. Alpha 1 times alpha 1 you get alpha 1, etc. So you can see that both tables are equal, U10 and automorphisms of Z10. And knowing this, I leave a last theorem that I'm going to leave it without a proof. If anybody wants a proof, can ask me. I can do another video. So the theorem says the automorphisms of Zn are isomorphic to the units n. So for every positive integer n, automorphism of Zn is isomorphic to Un. The proof is more or less the same as I did before, taking alphas to 1 of alpha. It's really easy.